So for this lab, we're going to be analyzing the change in mechanical energy from one point to another. We're going to toss a ball vertically. So we will see a shape that looks like this. And the goal of the lab will be, if you're given the gravitational constant, the mass of the ball, and the initial velocity as it goes up, it wants you to calculate at what height will that ball stop moving upward. In order to do that, we're going to analyze this from the point of view of energy. We're going to say that mechanical energy at the beginning, ME1, is equal to mechanical energy at the end, where we set the initial throw down here as scenario 1 and the height of the peak as scenario 2. Okay? And that means that mechanical energy is the sum total at any given point of potential and kinetic. So at the beginning and end, it's very easy to see that these are equal. And in the middle, it's kind of difficult. We're going to actually look at that relationship as we go. So potential energy in the first scenario plus kinetic energy at the first scenario is equal to potential energy in the second scenario plus kinetic energy at the end. Now, for convenience, we'll set the ground level it comes from at 0. Now, we do this so that when I plug in values, numbers work well. I'll also give you that for the examples we work here, G will equal 10. Okay, that just will be easy to deal with. That will not be the case for your lab, but this is to practice the math process. All right, so that's 10 meters per second squared. So we know two statements because now we've got an equation, but that doesn't necessarily help us if we don't know what these values are equal to. So I'm going to make a additional statement that potential energy is equal to what? What is potential energy equal to? mgh, where this is mass, this is the acceleration due to gravity. For the problems we do here, it'll be 10. It will give you a specific acceleration due to gravity in the lab. And then the height, well, that's what we're going to solve for. All right, and we also see that kinetic energy here is equal to 1/2 mv squared, where m is the mass of the object and v is the velocity of the object at any given point. So in the example we see here, let's see when we start in initial position. All right, so we're going to write this down here. PE, this is mgh. We'll call this 1 plus k, or we'll say 1/2 mv squared. And we're going to call this 1. So these are the first two scenarios. This is our mechanical energy starting out. All right, so it doesn't matter what the mass of the ball is. Let's just consider the potential energy at the beginning. What height does the ball start at scenario 1 right here?
0.
At 0. So if I start at 0 height, how much potential energy do I start with? 0 joules. All right, so this is how we're going to start our problem, because we will start with kinetic energy. The ball will start moving upward. So I'm going to give the value of mass to be 2 kilograms. I already stated that G here will be 10. And then I'm going to say that the velocity that we start with is 6 meters per second. These numbers really don't matter. I'm just pulling them out to have something to plug in. So we have 0 joules here in potential energy. So how much energy do we start with in kinetic if we have a mass of 2 and a velocity of 6? Well, let's look at this equation. It says 1/2, that's 0.5 times 2. What's 1/2 times 2? That's just 1. So that'll be 1 times the velocity squared. What's 6 squared? 36. So 1 times 36 is 36. So we start with 36 joules of kinetic energy. So this is the total amount of energy that this ball starts with. So we start with 36 joules of energy. This is the initial state. So initial energy equals 36 joules. All right. This is also equal to final energy. Well, let's just look at our scenario here. At the peak of a parabola in this motion, what is the velocity right there as it turns around?
0.
That is the instant where it stops. This is the instant where velocity is equal to 0. If that is the case, then we'll have this equal to mgh2 plus 1/2 mv squared 2. So this is just the expanded version of this red equation here. This is 2. All right, so let's look at that. What's the velocity at that height right there? It's equal to 0. So velocity is equal to 0. When I plug that in, what's my kinetic energy at the top of the motion? There is none. It is 0. So it will be this mgh plus 0 joules. So just mathematically, I want you to think, what does the potential energy at the top of that peak have to equal for this mathematical statement to be true? It has to be equal to 36 joules. Now, I can say that and still not know how high it went. So our goal here is now we've got the statement that mgh2, the second height, because mass didn't change and gravity didn't change, is equal to 36. I want to know ultimately how high did the ball go? So how do I solve for this? Because now I'm going to take this statement here and I'm going to pull it out to the side just so that we can very visibly see it. I'm going to do it in red over here. We're going to state that mgh2 equals 36 joules. All right, so how do I solve for h? How would I get rid of what's attached to h here? I divide it by what?
Yeah.
Mass times gravity. So I divide by mg because that's what's connected to h here. So if I divide the whole thing by mg, I find that h2 is equal to 36 joules. Well, what's the force? This is the force of gravity, right? mg is fg. So that's mass times gravity. We're going to call gravity 10. We're going to call mass 2. So 2 times 10 is 20. All right, so let's do that calculation. We've got 18 over 10, which would be 9 over 5. I don't know what that number comes out to be. It's
36 divided by what?
it's just under 2.
It's 1.8.
Yeah, it's 1.8. There we go. So this goes 1.8 meters into the air. So that would be our final answer. That would be our goal here. So the calculate, I'm going to do one more with you. So now let's do, we'll continue this one and finish this one. We'll do one more quick practice now that we've seen it. And then we're going to go do the lab. The lab should only take you about 15 minutes. Yes. I mean, the shortcut is knowing that at 0 height, potential energy equals 0. At maximum height, kinetic energy equals 0. So you can ultimately just say that kinetic energy initial is equal to potential energy final. And then you'd immediately have 36 equals mgh2. And you'd skip all this middle step. I'm just showing you where it comes from. All right, so when we do this problem, that's how you would set it up. You'd say that initial energy equals final energy. It has no potential to begin with, and it has no kinetic to end with. So that means that kinetic energy initial must equal potential energy final. And that equation would get you straight here. It would take you straight here. All right, so let's just look at the reverse of this. I said that negative work due to gravity causes it to slow down. It'll transfer all of its kinetic energy into potential energy. And then once it starts to turn around, gravity starts to do positive work on the object and it starts to pull it downward. All right, so the amount of positive work it will do would be the force times the distance over which it will fall. Well, we now have a distance, right? It went up 1.8 meters, correct? So if it went up 1.8 meters, how much work can gravity do? We'd say 1.8 times 20, which would give us 36 joules of energy. So if we set this second, we're going to split it right here. We're now going to call this 3 and 4. When it hits the ground, it'll be 4. Right before it hits the ground, right before impact, it'll be 4. So I want to see what's the translation here. What kind of energy does it have at scenario 3? potential energy. It has exactly 36 joules of potential energy. That's what we calculated just a second ago. So how many joules of energy would you expect to have at the end in kinetic if the height is equal to 0? You'd expect it to also be equal to 36. So if it's equal to 36, how fast will it be going? All right, so if we think about that, we started with the idea of 1/2 mv squared equals 36. That was 1 times 36 because it's 6 squared. So we would work that backward. We'd say that 36 is equal to 1/2 mv squared. 1/2 m is 2. So that would be divide by 1, take the square root, and we find that final velocity here is equal to 6 meters per second. Now it's negative because it's falling. But this is just a mathematical proof for something we saw way back in kinematics, that the initial velocity of a thrown vertical object is equal and opposite to its final velocity right before impact. So if you throw it up with 6 meters per second of energy, or of velocity due to kinetic energy translating into potential and then retranslating back into kinetic, you'll have the same energy you started with when it comes back to your hand. It'll just be directed down instead of up. So that kind of explains projectile motion in an energetic sense. What I'm going to do is I'm going to erase all of this. We're going to keep the scenario, change the numbers, and then we're going to go practice for real. Okay. All right. So set it up again. This is going to take me just a second. There's all kinds of writing here. All right. So we found 1.8 meters last time. So we're going to do the same thing. I'm going to give you a mass of 2.7. All right, so we've got a mass of 2.7 kilograms. Go ahead and write that down. We're going to throw it with a velocity of 4.85 meters per second. All right, we're going to keep this statement. We can reduce that statement, as I said earlier, that kinetic energy initial is equal to potential energy final. So kinetic energy initial is going to be 1/2 mv squared equal to mgh2. This is how we're going to set it up. All right. So I told you mass is equal to 2.7, right? 2.7 kilograms. And then velocity here is, I said 4.85 meters per second. All right, now I'm going to throw you for another loop. We're going to make gravity 8. Yes. That's just saying the second height, because initial height here, height at 1, this first scenario is 0. And remember that we said that this is 0 and this is 0. So I've just reduced it to the 2 middle terms here because you asked for a shortcut. There's your shortcut. All right. So we've got technically 0 plus this equals this plus 0. So I just took the zeros out because height at the initial is 0 and the speed at the top of the peak here is also 0. So those two terms go to 0. All right. So what's my mass? It is 2.7. I got to do this one on a calculator. I don't know how to square 4.85. Not in my head. All right. So I want you to go ahead and calculate initial energy. If you haven't already, type it in because you'll have to do this for your lab here in just a second. I'm giving you weird numbers because this is indicative of what you're going to see in the lab. So we've got the velocity squared times the mass times 0.5. All right, I'll give you guys a second to calculate that. Excuse me. All right, what do we find? What is the initial kinetic energy of this ball? There we go. So 31.76. There's a 31.76 joules of energy here. So this is how much energy the ball will have at its highest point. We want to figure out how high it is. Now I want to remind you that G is no longer 10, so you can't use 10 there. So we're going to state the same thing we did last time, that this is equal to mgh2, where m is 2.7, g is 8, and we don't know h2. So how do we solve for h2? Divide by mg. Well, what's mg? 2.7 times 8. Go ahead and do that.
3.7.
It's going to be 21.6. And that would technically be newtons because that's mass times acceleration. So we have 31.76 over 21.6 equals the height. All right, so go ahead and calculate that.
1.47.
So this is equal to 1.47 meters high. So let's think about this just mathematically. What was the previous answer in height? 1.8 meters. Let's think about that though. You had a 2 kilogram ball thrown at 6 meters per second. Which affects your kinetic energy more, velocity or mass? 1/2 m or v squared? Which one would grow faster? V squared. So changes in velocity have the biggest impact on kinetic energy. And notice that the velocity went down even though the mass went up. All right, that being the case, that's why we see a lower height and a lower initial energy, because we have less speed, less energy went in, so we'll get less height for that ball. Now, I want to show you something that's kind of interesting, and it might help you here. If we have the statement 1/2 mv squared and mgh, what do they both have in common? M. That means that it does not care about mass. If you multiply the mass in, you'll eventually divide the mass out. So you can actually have the statement 1/2 v squared equals gh. And this is just as true as the previous one. So that means that h is equal to v squared over 2g. So you asked for a shortcut. That's technically the shortcut. We've seen this before, but this statement right here comes from the idea that mass is in common. So you could take mass out of both these equations by dividing both sides by mass. You're left with 1/2 v squared on the left and gh on the right. If you're solving for h, you just divide over g. 2 was in the denominator, so that's why it's 2g. 1 was up here, so it's v squared over 2g. If you plug your numbers given into that, it will immediately spit out your height. So the only thing I'm going to warn you about, because you need the rest of the time to do the lab, it will give you, I think, values. Make sure that you use the right unit. So let's go over there together. So let's head over to that. So what you're going to do is you're going to do this simulation. So I'm going to pull it up, make sure you guys can see it. You need to pull it up as well. This will be due by, I think, 11:59 tonight. If you don't finish in class, you should be able to finish in class though. So you open this up, it's a physics aviary. So you're going to be presented with an object being thrown straight up into the air. You should use your ideas of energy conservation to determine the maximum height. Pay careful attention to the energy graphs. All right, that'll just help you understand conservation of energy, that mechanical energy, the green one, stays constant, that gravitational potential and kinetic both trade. So it gives you initial values. Yours will be different than mine, but notice it gives you mass, initial velocity, and gravity. So you're going to enter your name. You need to enter your name. Go ahead and do that. This is how I know it's you. This is individual to everyone. So everyone has to do it. Then you're going to predicted height in centimeters. It gives you meters per second per second. This will produce a height in meters. You'll then convert to centimeters by multiplying that number by 100. So remember how I got 1.8 meters in the first example? That's 180 centimeters. 1.47 is 147 centimeters. So the number you get as meters needs to be converted into centimeters. You're going to predict that, and you need total energy. Total energy is the energy you started with. All right, so for mine, we're going to say, oh, one last statement, and you must do this. Mass is given in grams, not kilograms. You have to convert to kilograms by dividing by 1,000. It will generally give you a 3-digit gram. Put a decimal in front of the first digit, and that's what it is in kilograms. So this is 0.359 kilograms. So when you run it, you'll make your prediction. It'll put the bar where you predicted it to be, and then it's going to see whether you're right. And then it's going to let it fall back down. And so you get immediate feedback if you are correct. If you get it wrong, do it again, submit the correct version. All right, so this is the screenshot I'm looking for. After you've completed it, if you got it right, it's going to say, congratulations, you're correct. So it's going to give you your predicted and the actual value. So do you guys know how to take a screenshot on your laptop? This is how you'll submit your answer. You'll have this version with your name up top. It'll say, congratulations, you're correct. You'll take a screenshot image of this and then upload that screenshot's file to the Canvas document.